Welcome to today's lecture. Today we're going to start seeing the Fourier transform. Now, this is going to be an introduction to the Fourier transform, but the Fourier transform is something that will accompany you throughout your degree. The Fourier transform is possibly, is one of the most important pieces of math that you will use in your electrical engineering in terms of signal processing. It's extremely important in physics. It's extremely important in many fields of physics, from optics to quantum mechanics. It's crucial, it's at the core of it. The Fourier transform is immensely important in math, in physics, and engineering. So, hopefully, you will enjoy this and try to extract as much as you can and learn as much as you can, because this is going to be important. I mean, it's not the last time you're going to hear about it, but it's the first time. So it's really, really important that we try to understand well what's going on. Now, to understand the Fourier transform, let's first understand properly what we were doing with Fourier series. With Fourier series, we had some function, say something like this, right? And then we said, right, if I want to reproduce the function in this interval, say that I call this t, right, this interval here, then the function, I know I can I can actually exactly write it as a Fourier series. The Fourier series I get with the periodic extension, right, which would be like that, and same on the other side, and you say, right, the function here is not equal to the function f of t, right, but within this period it will coincide exactly. And then say, okay, if you want to reproduce more of the function, well, what you should do then is increase this period, right? I can do it like that. If I do it like that, and this is the period t, then the periodic extension would be something like that, and then something like that, and so on and so forth. So I'm reproducing more of the function. So the reasoning is, maybe I can take this t to infinity and then reproduce all of the function. What would happen then? Now, really important to realize what the Fourier series is doing. I have a function f of t that is not oscillatory, but suddenly I write it as a sum of oscillatory functions. So cosines, I can write like that, an cosine n omega t, and b n cosine sine n omega t, right? And a0, but I put it inside here. Why not? So now you realize that this function f of t is made of components. Remember the algebra part of it. A vector in the space of functions. Every vector is a function with infinite entries, an infinite dimensional vector, right? And then this cosine, an infinite entry, is a continuum of entries, if you want. And you see that it's decomposed in terms of sines and cosines. And each of those cosines oscillates with a frequency omega sub n t, which is omega sub n is n times omega. Right, so there's a basic frequency omega, and then higher summands in here oscillate with higher values of omega. That's what I call omega n. So this would be the sum of the cosine of omega sub n t and sine omega sub n t. So a sum of sines and cosines. All right. So it's kind of cool because it's telling you that functions contain different frequencies. And we will talk about pictures, we'll talk about music when we understand better the Fourier transform. All right, but these are the main keys that we want to introduce here. Now, let's go back to the complex Fourier series. Let me quickly erase this. So we have here the Fourier series of f of t, the complex Fourier series. And this thing, remember, omega times n is what I call omega sub n, defined here. And here I have the Cn, the calculation for the value for the coefficients of this Fourier series. And I took this value by taking t0 equal t minus t over 2, right? If it's t0, t0 plus t, if t0 is minus t over 2, I get that. Now, let's see what happens. I'm going to tell you where the Fourier transform kind of comes from in terms of the Fourier series, but it's not a rigorous proof in any way. It's just to give you an idea how one becomes the other when you take the period to infinity, all right? It's not a rigorous proof. In fact, defining the transform has more nuance than that. But it's as a kind of intuition physics understanding, if you want, you will get an understanding of where it comes from. Again, of course, it's not rigorous, and therefore there would be like, oh, but then isn't that divergent, and so on and so forth, okay? So bear with me in terms of, let's try to build an understanding. And at the end of the day, the Fourier transform I will give you as a definition, okay? But let's get some understanding about what it is. Now, look at this. What is the distance in frequency? So when I sum a cosine of n omega t, the first one is cosine of omega t, the second is cosine of 2 omega t, the third is cosine of 3 omega t. Cool. How far away are they in frequencies? Well, you see, omega 2 minus omega 1, the difference between two consecutive frequencies is 2 pi over t. So, the larger the period, the closer in frequency the two summands are. You see, the elements of the bases, those cosines are more similar to each other. They're lumping together. As I make t go to infinity, the different summands are lumping together in the space of frequencies. And then you see, when t goes to infinity, the distance between two consecutive frequencies is 0. So it's infinitesimally small. As I make this infinitely big, the difference between two frequencies becomes infinitesimally small. Now, because it becomes infinitesimally small, then we see that the variable, I wrote here a variable n over t, let's call this variable k for now, although again, we will talk a little bit more about that. N over t, k is a discrete variable in the sense that it has values 1 over t, 2 over t, 3 over t, right? And as n runs, right? As n runs up, the n over t, right? K, which is n over t, runs up as well in discrete jumps. Now, when t goes to infinity, this thing varies. So imagine that this is very, very large. So n over t is infinitesimally small, moving in n, because again, n is not that n is fixed. N runs all the way from minus infinity to infinity. So you have like infinity over infinity when you run over. That is the definition of a continuous variable, right? You get something that varies from minus infinity to infinity that gets really big, divided by something that also gets really big, in a way that it compensates each other. So this, I define a continuous variable k, which is precisely the choice that makes this compensate each other. So this has finite value, real values, right? When t goes to infinity, and that means that this thing will be becoming a sum between elements that are lumping together on a continuous variable n over t that is what is running through. So it's basically going in a way from n over t. I can make the change of variable n to n over t, and that would be kind of a sum n over t, or k if you want, right? I'm not gonna write it, but it's gonna be a sum over the values of n over t running in a continuum, right? Running from minus infinity to infinity. This thing is what you saw as a Riemann sum, something that yields the integral. There are some questions one may have if it's not exactly rigorous, but then you can see that when I make t go to infinity, this sum is becoming a sum that the summands are lumping together close to each other, and the variable that was going in jumps, n from minus infinity to infinity, now becomes a continuous variable k that runs in a continuum. So the analogy that we're doing here is that, well, f of t, in the discrete case, we call it sum n equals minus infinity to infinity, cn e to the I omega n t. Now that, this is say in the series, this is in the transform. So in the series and in the transform, the series now is going to correspond to something that is like an integral from minus infinity to infinity of some continuous variable. Maybe I'll write here 2 pi n over t, something dk, then whatever, let me just write here with a red color this cn, because cn is no longer a cn, now it has to be a function of k. It was a function of n, but I changed to a continuous variable, then it's no longer there. It's n over t, so that thing should be a function of k. Function of k. And then I get here the exponential of I, 2 pi n over t, which is k, times t. All right, so let's figure out what this Cn is. Now, Cn here, I have as an integral of f of t, and if I do the change to the continuous variable, now I do have the problem that this is divided by 1 over t, all right? And that you say, oh, when t goes to infinity, right, this goes to 0. Yeah, but let's bear with me to see what this covers. So again, I'm not telling you that you get the Fourier transform out of extending the Fourier series to infinite period, but I'm telling you that, yes, you get that, you just need to be careful with the math. You need to do it in a clever way. So it requires, to do it properly, it requires a bit more math, and by a bit I mean a lot more math than you have seen and probably you will see in your degree, unless you actually take pure math courses. But I think that it's enough, you're mature enough to get the idea. Yeah, there are some subtleties in here, in a way. But these subtleties in here is the 1 over t. If I were to remove, imagine the 1 over t from here, and you say, can you remove it? I go, no, definitely not. And then that's why you have to be careful when you define it. But again, bear with me. So if I were to not write this, the Cn would be proportional to, as t goes to infinity, integral from minus infinity to infinity dt, and then I get the function f of t, and then e to the minus I 2 pi kt. Aha! So this thing is no longer, this thing is proportional to something that is certainly a function. Is this a function of t? You will very quickly say, no, it's not, because t is integrated over. It's a dummy variable, all right? T could be called Joshua. It is, however, a function of k. This thing, let me call it capital F of k. This capital F of k that I have here, right, is what is going to substitute Cn in here. So it would be a capital F of k. And now, this will be f of t. And of course, in the series, what I have is the coefficient that was equal to 1 over t integral minus t over 2 to t over 2 dt f of t e to the minus I 2 pi n over capital Tt. That thing now becomes this f of k that is equal to the integral from minus infinity to infinity dt f of t e to the minus I 2 pi kt. Now, this is what we're gonna define as one of the possible, which will come later, Fourier transforms of f of t, in the same way we did with the Laplace transform, remember? So the Fourier transform is gonna be an integral over k multiplied by a phase like that. And this is the inverse, this thing is the inverse Fourier transform of f of k. You see? We can define now, and then again I'll write it once. I can say, well, by definition, f of k will be the Fourier transform. So I call it the, I'm doing Lagrange, no, Lagrange, Legendre. Fourier transform of f of t, which I call also equivalently f of k, and this thing is the integral from minus infinity to infinity of dt f of t e to the I 2 pi, oh, I'm missing, no, I'm not missing anything, to the I 2 pi kt. And then I know that the inverse Fourier transform, and thus the Fourier transform of the f of k, which is the same as f of t because it's undoing the Fourier transform, this thing is equal the integral minus infinity to infinity f of capital F of k. Alright, and then, oh sorry, dk capital F of k e to the minus I 2 pi kt. So that would be a Fourier transform and that an inverse Fourier transform. Don't copy, this yet, this is just to give you an idea because we're going to talk about the many ways of defining this Fourier transform that we can have. But you can tell that these definitions are, at least if I take this as a definition, it's not coming from the Fourier series, it's a definition. You can tell that it's something like taking the period of the Fourier series to infinity. Modulus some mathematical hurdles that you have to deal with, but there are very clever mathematicians that can deal with that. And then you see that it really comes from something like that. You get an integral, of course, if I am one of the first people that want to do things rigorously. But the fact is that with the math we have so far, we cannot actually, so far as we've seen in your courses, right? We cannot actually do it properly in enough time, but this is fast enough. It's a compromise between doing it fast and still showing you how the series becomes integrals and the series becomes a transform, all right? And the series becomes a Riemann sum, and this that was already an integral becomes an integral from minus infinity to infinity, etc. Now that we've introduced the idea of how the transform goes, we can tell, I can do changes of variables, right? If I start doing change of variables here, imagine that I do a change of variables that is, I don't know, I define a new k with k tilde, which is 2 pi times k. Well, if I do that, this thing becomes, well, I k tilde t and nothing else, and this one becomes, well, k tilde here, but then you get the differential of k, so then you have a 2 pi also in here, right? So that would be 2 pi in there. So you see, there are different ways of defining the Fourier transform by doing changes of variables. What do we call the frequency domain? Now this k is going to be, and we will discuss it, the real deal, the real frequency domain. If in your courses in electronics, I don't know if you do it, but if they tell you that doing Laplace transform, you go to frequency domain, that's not quite true. We will discuss what it means because people say there must be a reason, but it's not true. What really goes to the frequency domain, the k domain or omega domain, whatever you prefer, that is the Fourier transform. The Fourier transform is telling you the components that a function has of the many different frequencies that make up this function. Now let's define the Fourier transform in this full generality and talk about the usual conventions that people take for the Fourier transform. Okay, the Fourier transform can be defined as follows. So this is the general definition. And the general definition is, well, all the possible conventions, all the possible definitions that you can have for the Fourier transform. And they differ in a normalization factor, and they differ in the interpretation that we have for the variable k, all right? So this is the general definition. The general definition is that the Fourier transform of t, which we will call capital F of k, is the integral, the square root of b, modulus b, or absolute value b, divided by 2 pi 1 minus a, and then the integral from minus infinity to infinity dt, f of t e to the I b kt. This b here is what multiplies the k, and it's also outside in a square root. And the inverse Fourier transform corresponding to this one, if you make this choice, then the inverse Fourier transform would be on this way. This covers all the possible conventions, and a and b could be any real numbers. Now, there's a handful. I have here the 4 most popular conventions. Different fields tend to use different conventions. Why? I have no freaking clue. This is the same in thermodynamics. Engineers pick one convention for the sign of work. So what do you think? Work done to the system should be positive or negative? Heat coming out of the system should be positive or negative? Well, physicists and engineers disagree on that. Anyway, those are conventions. I'm not going to get into that. Those are conventions, okay? That's same as the Fourier transform that we use. As long as we know what we use and we're consistent, is fine, okay? What we call each. But the fact is that mathematicians tend to like one, physicists tend to like, engineers tend to like another one, and physicists tend to like 2 of them, depending on what you do. Anyway, whatever. So the point being that those are the 4 most popular ones, and we're gonna use in our course the one, I give you the reasons why, we can choose whatever, but the one that we will use is the last one that we will see, and I'll give you reasons why we're gonna use that one. Anyway, first, you see that some of them have b equals 1 and others have b equal 2 pi. Well, picking b 2 pi or 1 is how do we interpret k? As a frequency, like this linear frequency, or an angular frequency? Well, that is, again, up to us to do. Angular frequency is more natural. The angular frequency is that what goes inside the cosine and multiplied by t. For a physicist, it would be more natural. Anyway, this convention is pretty common. It's pretty common in engineering, actually. And also common, some mathematicians like it as well. It's nice in terms that it is symmetric, like this. It's also unitary, but we're not going to talk about that too much. Maybe until the end, what I mean by unitary. But it's nicely symmetric between the transform and the inverse transform, right? Another possible choice is picking a minus 1, b minus 1. This is favored by some mathematicians too. Also, engineers sometimes use this one, which is a bit funny. The direct transform has 1 over 2 pi, okay? In fact, the ones that engineers like the most is with a 2 pi in here. So B equals 2 pi. It's depending on the engineers, right? Anyway, so this one has a 1 over 2 pi in the transform and nothing in the inverse transform. Also, the signs are a bit backwards as compared to what is more natural for me. But again, it's a valid convention. It's substitutions. You see, substituting values of B and A in here. This one, this is one that is also pretty common in physics, where we have nothing for the direct transform. It's kind of it's like the lazy option. That's what's common in physics. This is the transform. Oh yeah, a positive sign and nothing in front, and I don't care. And then that means that you have to pay the price at the inverse. You need to care and remember that it's 1 over 2 pi, and then with a negative sign. Now, the one we will use is the preferred one in physics. We're going to use this one in the course. That's why it's purple rather than black, which is A equals 0 and B equals 1. Now, after using that, you don't need to remember this anymore. You only need to know that it exists. There's an infinite number of ways of defining the Fourier transform. We're going to use this one. It's super common everywhere. It's also unitary. There's only 2 choices that are unitary, or 2 families of choices. That one does the other one. But this is nicely symmetric as well between transform and inverse transform. And also you see it's the same prefactor, 1 over root 2 pi, and then positive for the direct transform and negative for the inverse transform. That capital F of k is the Fourier transform of f of t, small f of t is the inverse Fourier transform of capital F of k. Notice always, right, how this is not a function of t, it's a function of k, t is integrated over. Likewise, this is a function of t, not a function of k, k is integrated over. They are dummy variables of integration. All right, now that we've learned what is the right Fourier transform, again, all of them are the same, I guess, equally valid. You just need to be consistent with the convention you choose. I'm going to take that one. Because I'm a physicist, because I'm a mathematical physicist, and because it's nicely symmetric, because it's unitary. What do you mean by unitary? Well, I mean that the norm of the functions is equal to the norm of its Fourier transform. But we will learn more about that when we see Parseval's theorem for the Fourier transform. All right, for now, let's leave it as is. Now, the next thing we're going to do is learn some properties of the Fourier transform before starting to compute some examples. All right, let's start proving properties of the Fourier transform that are going to be useful for us to compute, same as we did with the Laplace transform. Now, I put the definitions here, definitions what we're going to use throughout the course. So the Fourier transform of f of t is 1 over root 2 pi minus infinity to infinity integral of f of t times e to the I kt with respect to t. Of course, the inverse, right, which the inverse Fourier transform. So if I apply the inverse Fourier transform of the Fourier transform, I recover the function, original function I have. It's knowing the Fourier transform is the integral, same as before, but with a minus in the face, in the exponent. All right, the first property is linearity. Now that one, we don't require to prove it because we've already proven it. We've done a very similar proof. The linearity of the integral makes the Fourier transform linear. If the integral is linear, the Fourier transform is a freaking integral, well then, of course, the Fourier transform will be linear, right? Now that's basically, the Fourier transform of the sum is the sum of Fourier transforms and also a scalar factor multiplied. So A and B, I'm going to write them here as real numbers. Alpha and beta are real numbers, right? So constant factors can come out of the Fourier transform, and unsurprisingly, they can come out of integrals, right? And the Fourier transform of the sum is the sum of Fourier transforms. Well, the integral of the sum is the sum of the integrals. Proved, all right? Okay, the second property, the shifting property, tells me that if I know that f of k is the Fourier transform of f of t, then the Fourier transform of the same function, but translated to the right, the Fourier transform of t minus t0, is the same Fourier transform as for the function without the translation, but multiplied by e to the I k t0. All right? Wonderful. So, let's prove it, shall we? First, we write the definition. f of t minus t0, by the definition there, is 1 over root 2 pi integral minus infinity to infinity dt f of t minus t0, right, substituting, e to the I kt. Now, what we're going to do is a change of variables. So I'll write it here. The change of variables I'm doing is t tilde equals t minus t0, which means that t is equal to t tilde plus t0. Also, it means that dt tilde equals dt, because t0 is a constant. All right, let's apply the change of variables. So 1 over root 2 pi, limits of integration. Okay, when t goes to infinity, t tilde also goes to infinity. T0 is just a constant value. So, and when t goes to minus infinity, t tilde goes to minus infinity as well. Nice. dt tilde, differentials are the same. Now I get f of t tilde, and now I get e to the I k multiplying t tilde plus t0. All right. Oh, but nice enough, this thing is e to the I k t tilde times e to the I k t0. Isn't that wonderful? Right, because e to the I k t0 is not a function of t tilde. So it's a constant with respect to this integral. It can come out of the integral. I can write e to the I k t0, taking this factor out, multiplying 1 over root 2 pi integral minus infinity to infinity dt tilde f of t tilde e to the I k t tilde. And this, my friends, is the Fourier transform of f of t. And same as I predicted with the Laplace transform, I'm pretty sure that there would be some people that would be like, no, this is the Fourier transform of f of t tilde, right? You need to undo the change of variables. And I would say, aha, no, because, it's satisfying to say that, huh? Because I would not say that, I'm nicer than that. And this is a caricaturist version of what I would do. I may think it though, but don't tell anybody. Just kidding. Or am I? Anyway, this function, this thing is not a function of t tilde. Why? Because t tilde is integrated over, it's a dummy variable. I could call it Joshua, okay? So that would be, this thing does not depend on Joshua. So this thing is the same as if I call everything t or if I call everything t tilde. It's certainly true that this is also the Fourier transform of f t tilde, or also Joshua if I want. But this thing does not depend on t tilde or on t or anything. That is integrated over. It's a dummy variable of integration. Okay? Super important. And if you have doubts about that, or jokes aside, if you don't see it, you have a problem with that, please do ask me, because this is important. I don't want it to be put off by that. There will be people that would say, it's a reasonable question to have. It makes sense if you haven't seen it before. It's important that you get used to it though. So, again, this is the Fourier transform of t, okay? Doesn't matter that it's called t tilde or whatever else. I can call it Joshua if I want. It's a dummy variable. Wonderful. And it's a function of k only, not a function of t, right? So this thing is the same as f of k. Right, wonderful. So the final step, we arrived. This is k, t0, capital F of k, and we have proven the shifting property. Nice. Okay, so let's do another property. All right, this one, modulation, or also called shifting property in the frequency domain. Basically is if I take a function f of t whose Fourier transform is f of k, then if I multiply by an oscillatory function like that, e to the I omega t, I shift in the frequency domain. Keep in mind, the real part of that would be multiplying by a cosine, the imaginary part would multiply by a sine, okay? So it's definitely multiplying f of t by an oscillatory function. All right, this is an interesting and cool property, and let's prove it. So, we go to the definition. Oh, Legendre wants some screen time. But it's not gonna get it. Not now, Legendre, not now. All right, e to the I omega t, f of t. Right, well, let's write the definition. That is 1 over root 2 pi integral from minus infinity to infinity dt e to the I omega t f of t e to the I kt. All right, easy enough. We can rewrite this as follows. Minus infinity to infinity dt, let me put this exponential in here, f of t exponential of I k plus omega t. And now we compare f of k, wherever the variable k is whatever appears in the exponent multiplying t. You see, that's the only instance where k appears. Wonderful. So this is the same as substituting the value of k by k plus omega. So this thing is exactly the same as fk plus omega, because that's the definition of fk plus omega. If I write k plus omega here, I have to write k plus omega here. Because this is not a dummy variable, unlike the t tilde and so on, k is not integrated over. This is the real dependence of the function. Okay, you see the distinction? Wonderful. So this is as simple as that, and it's proved. All right, this is a very important property, okay? I don't want to box it because I'm about to erase it magically, but it's an important property. Okay, remember it. Let's see the next one. The fourth property is called scaling, the scaling property. Basically says that if I have the Fourier transform of a function multiplied by a number, the variable, a function of the variable multiplied by a number, if I rescale time, you can think of it as changing the units of time, right? Multiplying by a conversion factor, something like that. Then the Fourier transform is affected like that, 1 divided by the absolute value of that r you multiply by, and then the Fourier transform is now the function of k divided by r. This is important, and let's understand what our rescaling is. What does that mean? So if this is f of t, what would be f of, say that r, it's equal to 2, what would be f of rt, which in this case would be f of 2t. If I were to draw f of 2t, the function shrinks. So what happens now is the function has a y of a over 2. Okay? Let me just write it like before, like that. So when I write the function of f to t, it reaches the end of the function earlier. It shrinks, okay, in t. This is t. And likewise, if I have a function f of t, and now I divide by r, when r is equal to 2, so that is f of t over 2, that expands. What I have now is whatever double that is, so I don't know, expands like that, and now this width, sorry, as I wrote it before, the width is 2a. All right, that's important, right? Again, if r is larger than 1, multiplying the argument will shrink it. If r is smaller than 1, well, multiplying the argument would expand it. Now, if r is larger than 1, divided by r would expand it, and multiplying by r would shrink it. Okay, it's important that we get those pictures in mind. All right, now that that's clear, let's prove this. So it's kind of interesting, because if you shrink the function, the Fourier transform gets expanded. This is so cool, and we will see it in action because it's related to something called uncertainty. Have you heard about Heisenberg uncertainty principle? As in, like, you cannot know the position of a particle with full precision and then know the momentum of the particle. If you know it with full precision, you have full ignorance about momentum. And if you know the momentum with full precision, I mean, it's ideal. You never can get full precision, but with a lot of precision, then you don't know where the particle is. In fact, the particle is everywhere. That Heisenberg uncertainty principle that you may have heard, we're gonna prove it here with the Fourier transform at the end of the course, at the end of the block. So this is related with the uncertainty principle. Basically, if I make the function, one of the functions of time, something that is longer in time, if I make it longer in time, it shrinks in frequencies. And if I make it longer in frequencies, it shrinks in time. Looking forward to talking about that a little bit more. For now, let's prove it. All right, first thing, write the definition. And the definition is 1 over root 2 pi minus infinity to infinity dt f of rt e to the I kt. All right, let's do a change of variables. The change of variables I'm going to do is the following. T tilde is equal to rt. And that means that dt tilde is equal to r dt. All right. Wonderful. So that also means, if I solve this, that t is equal to t tilde divided by r, and dt is equal to dt tilde divided by r. All right, let's do two cases, shall we? Let's do the case first, r larger than 0. I mean, I could do both at the same time, but it's, for the first time you see these kinds of proofs, it's better to separate into. If r is larger than 0, then, okay, this is equal to 1 over root 2 pi, and then when t goes to infinity, t tilde goes to also infinity. That's nice because you know the r is positive, so definitely infinity to infinity multiplied by something positive, still infinity. And when t goes to minus infinity, same thing. T tilde goes to minus infinity. Now I write the dt, which is the t tilde divided by r being positive. And then I get f of t tilde. And then I get here e to the I k, and then t tilde divided by r. All right, wonderful. So I realized of the following. I can take the r outside of the integral because, right, it's a constant factor. And I can put the r divided by k. So this is 1 over r being positive, 1 root 2 pi, then integral from minus infinity to infinity, dt tilde f of t tilde e to the I k divided by r t tilde. And nice enough, this is the Fourier transform of f of t, because this is a dummy variable, call it t tilde or whatever, but substituting k by k over r. So this thing here is the Fourier transform f capital F of k over r. You see? It's the same as the Fourier transform, but only where you see a k, write a k over r. Wonderful. So that means that in this case it's 1 over r f k over r, when r is positive. What happens when it's negative? Well, when it's negative, I get 1 over root 2 pi. Now, first, the limits, what I'm going to write here is I'm going to do something else. I'm going to write when, if it's negative, right, r, it's equal to minus modulus r, right? That's what it means to be negative. All right, so I'm going to substitute r, because it's negative, by minus modulus r, all the time that I see it. Okay, first, the integration limits. The integration limits are, when t goes to infinity, t tilde goes to minus infinity, because r is negative, so minus infinity on top. When t goes to minus infinity, t tilde goes to plus infinity. So it's swapping the limits here. All right. Then I get here dt tilde divided by minus modulus r. Okay, because you can't say that because r is negative. Wonderful. So now I have f of t tilde, and then e to the I k t tilde over r. Wonderful. So first thing that I do, I use that the integral ab of dt f of t, it's equal to minus the integral ba dt f of t. If I use that here, I can swap the limits, I get a minus sign, with this other minus sign cancels. I can also take the r outside of the, oh, I forgot the, no. I can also take the r outside of the integral because it's a constant with respect to t tilde. So I get 1 over modulus of r, and then that multiplies 1 over root 2 pi. Now with the right limits, minus infinity to infinity, swapping the limits gave me a minus sign that cancels with this other minus sign. So d t tilde f of t tilde e to the I k divided by r t tilde. And this thing is certainly the Fourier transform of, so the Fourier transform of f evaluated at k over r. Whenever you see a k, you write a k over r. So the result here is that is 1 over modulus r Fourier transform of k over r. Now we put the two together because this is a positive r. I can also write this if I want, because a positive r is always equal to its modulus, and there you go. Actually, r has to be different from 0 for this to happen, so I can say. But there you go, of course. It's proven. I proved the two cases, and in both cases is 1 over modulus r f of k over r. This actually encompasses the two cases, so wonderfully proven. Satisfyingly proven, I would say. All right, wonderful. Let's see a couple more properties. All right, this is the property of conjugation of the Fourier transform. So the Fourier transform of the complex conjugate of a function, so in mind the function is complex, the transform of the complex conjugate is the complex conjugate of the transform evaluated at minus k. And in particular, if f of t is a real function, which is a nice property to have that we're going to have a lot, because we're going to do a lot of real functions, then of course that means that f star is equal to f, so that would be the Fourier transform of only f, which is f of k, it's equal to f star of minus k, which is what I wrote there. All right, that is if f is real, because if it's real, it's its own conjugate. All right, let's go and prove it. So first, let's write the definition. The definition is that f of the complex conjugate of f of t, it's equal to 1 over root 2 pi integral minus infinity to infinity dt f conjugate of t e to the I kt. Now, what we can do is the following. I'm going to take the conjugate of this twice. So I'm going to write the conjugate of the whole thing. I conjugate outside. If I conjugate outside, I need to conjugate inside. If I do two conjugates, I do the same, right? Conjugate of a number, the conjugate of the conjugate, z star of star, it's equal to z. All right, so if I do it twice, nothing happens. T is a real variable, so nothing happens there, minus infinity to infinity. Now I have to conjugate the whole thing, f of t e to the I kt. Very nice. So, minus I kt. I have to conjugate the two things, huh? I have to conjugate the product of the two numbers. So that would be f without the star is the conjugate of f of t, and then e to the minus I kt is the conjugate of e to the I kt. All right, wonderful. Now that looks a lot like the inverse Fourier transform. And yeah, let's wait for the next properties. That's not the way we're gonna go. But what we get here is that I can do the following. I can do 1 over root 2 pi integral minus infinity to infinity dt f of t e to the I minus k t, all conjugate. And now this thing, it's certainly the Fourier transform of f of t, but writing minus k wherever there's a k. You see the real variable in there, the variable that exists in there, that is not a dummy variable. All right, wonderful. So what that means is that this is just f star of minus k, and we have proven the identity. Great. All right, so let's do another property. All right. This property, which is the property of time reversal, cyclic transformation, tells me that if I do the Fourier transform of a function twice, I get the same function with time reversed, with the variable changed sign. Now, this one is one that trips many people, okay? So, because it's conceptually complicated with what variables we go in. We're doing two Fourier transforms, so keep in mind that what we're doing here is the following. We start from the time domain. Let's call it domain. Variable t, and then through a Fourier transform we move to the frequency domain, the variable we call k, and then under a different Fourier transform we realize that we move to the under a different Fourier transform we move to the, if you want, the frequency domain of the frequency domain, and that is again t. So you see, what is frequency? Well, the inverse of time. What is the inverse of frequency? Well, time. But you can already tell from the definition, right, that a time reversal seems to be what related in a way, something about reverting t in the Fourier transform relates somehow direct and inverse. I mean, of course, it's not as simple as that. But it's important that we make clear what we mean. So generally, I would actually have to write something else here, because this is the time domain. One Fourier transform takes me to the frequency domain. One inverse Fourier transform takes me back to the time domain if I go that way. But if I do another Fourier transform, it takes me to whatever the frequency domain is of the frequency domain. And that is back time. Those are what we call conjugate variables by the Fourier transform. The Fourier transform swaps time to frequency, and then frequency to time again. Only that when you go back, you are going reverse in time. That's what we're going to prove, okay? So hopefully don't get lost from the different variables that we're going to be using, okay? And what kind of functions these are. That would be inside here an f of k, but then if I do it again, it would be an f of t tilde, but that t tilde, we just call it t again because it's the same domain, okay? It's not a different one. There are not many different, the t domain, then the frequency domain, you don't go back to a second order frequency domain because it so happens that the frequency of the frequency is time. If that makes sense? Units of time, seconds if you want. Units of frequency, second minus 1. Units of frequency, well, seconds again. You invert the unit, all right? Hopefully that makes sense. But if not, please do come to the review sessions and let's discuss it. Look forward to it. All right, let me erase this and proceed to the proof. All right, so I wrote here the definition. Well, the square, apply twice the Fourier transform to f of t. And what that means is the inside is f of k, and applying that, it takes me back to a function of t. Now, if I write this with definition of Fourier transform, so keep in mind, now the roles are changed. I call k plays the role of a time domain here, because we're doing a second Fourier transform, so we're going to the frequency domain of the k domain, which is k is treated as if it were t in here, and t is playing the role of k. You see how the roles are swapped here. All right. Now, that's what it is. But I also can write that the inverse Fourier transform of f of ft, which of course is f inverse Fourier transform of f of k, and that thing is of course f of t, using the definition of the inverse Fourier transform that I have here, that would be 1 over root 2 pi integral from minus infinity to infinity dk f of k e to the minus I kt. Now, this one looks a lot like that one. The only difference is a minus sign in there. Well, that's the difference. We're doing a direct transform versus an inverse transform. But I realized that if I want f of minus t, that thing is, well, substitute wherever you see a t, a minus t. This is 1 over root 2 pi integral minus infinity to infinity dk f of k e to the minus ik minus t. Oh, nice. But minus times minus is a plus. And therefore, this thing is equal to this thing here. Let's call it 1. And this is equal to 1. Wonderful. So that means that the Fourier transform of f of t is just f of minus t. Time reversal. Proved. Now, one nice thing to realize is that, okay, if I do the Fourier transform twice, I get the same function but time reverse. If I do it 4 times, if I do f 4 times of f of t, then I do get the same function because I do 2 time reverses. Right? And if I were to do it 3 times, 3 times f of t, it gets me f of minus k, right? Again, here the jumps are, first, from time domain to frequency domain, then back to time domain, then back to frequency domain, but with an inversion. And now, here, from time domain to frequency domain, then back to time domain with an inversion, then back to frequency domain with an inversion, which means I go back to the original function. All right, let's see the last relevant property that we're going to see. The transform of the derivative, something extremely useful. All right, so the seventh property is the transform of the derivative that tells me that the Fourier transform of the f derivative of f of t, it's equal to minus ik to the power of n, where n is the number of times I took the derivative, and times the Fourier transform of f of k, of f of t, which is f of k. All right. Now I'm gonna do it for the first derivative, but you're gonna see that for the nth derivative it's very easy to iterate, right? So please do it yourselves. It's gonna be obvious after I do it, hopefully, after I do it for the first derivative. All right. So what we're gonna do a trick. We're gonna take the inverse Fourier transform. Instead of taking the definition here, I'm gonna take the inverse Fourier transform of f of k. Right? And this thing, it's equal to f of t, of course, let's do it like, right, I'll write the definition of the inverse Fourier transform here. Minus infinity to infinity, f of k, e to the minus I, kt. And this thing is f of t. All right? So what I'm going to do is I'm going to differentiate this with respect to t. So I differentiate this with respect to t, d dt of the inverse Fourier transform of f of k. And I differentiate with respect to t here. This is 1, well, I should write, maybe I'll do one step. Okay, d dt of 1 root of 2 pi integral minus inf to inf dk f of k e to the minus I kt. And of course this is d dt of f of t, differentiating both sides with respect to t. Wonderful. Now I realize that the only dependence on t is in here, and the integral does not depend, is not with respect to t, so the differentiation can jump the integral sign and gives me on the left the following. It gives me 1 over root 2 pi integral minus infinity to infinity dk f of k and minus I k e to the minus I kt, where this thing, of course, is the time derivative applied to the exponential. And that thing is equal to d dt f of t. All right, so we have that. Now, what is this though? The nice thing that I have here is that now I can understand this as a new function. Let's call it f tilde of k. So what this is the inverse Fourier transform of f tilde. You see? Is definitely the inverse Fourier transform of f tilde, what I have here. So this thing on the left hand side is the inverse Fourier transform of f tilde, well, I'll write what it is minus I k f of k. And on the left, on the right, I have still d dt f of t. All that I have to do is take Fourier transform on both sides. If I take Fourier transform on both sides, I'll open wormhole to continue here. Open wormhole. So if I do the Fourier transform on both sides, then you just write everything. F of f minus 1 of minus I k f of k equals to the Fourier transform of the derivative with respect to t of f of t. All right? Now, the Fourier transform cancels the inverse Fourier transform, and we get the desired result. Fourier transform of d dt f of t, it's equal to, now just minus ik f of k. How nice is that? So this proves it actually, because if you do it again, if you do the second derivative brings you minus ik squared, right? Because you do one and then you do another. Every time you hit with a derivative, the exponential, you get minus ik. So I can actually generalize the proof immediately, writing an n here and an n here. And that means that when I take an n and an n and an n and an n, then here I get n times this exponent, all right? And then an n and an n. And that means I have the n here, the n here, the n here. And I get the n here, the n here, the n here, n here, n here, n here. And the identity is proof, because I know that if I hit, so the whole thing relies on the fact that if I hit with a dt, this thing's n time, all that I get is minus ik to the n e to the minus ikt. All right, that is what is done for this step. All right, this is the proof of the last property that we will see today. Now, the next day we're going to see some examples. We're going to understand more about the nature of the Fourier transform and the Dirac delta. We're going to go back to that and see how the Fourier transform factors in it. We're going to discuss about what conditions f should have in order for the Fourier transform to exist, just a tiny bit, because we need a little bit more of advanced topics beyond the scope of the course, but we can discuss them with intuition. And finally, we'll end with the uncertainty principle that I promised. All right? All that in the next lecture. and I'll see you there. Bye-bye.